Today we want to investigate the effectiveness of root finding algorithms on randomly generated functions to gain a valuable insight into the practical applicability of these methods. And in addition to that, we want to find the impact of the different seeds to have a varying problems domain in the algorithm. So in this challenge, we want to run a random function generator. We will begin by generating random functions using deep neural network or DNN. Given a seed, a set of random weights will be generated from the standard Gaussian distribution. These weights will then be applied to the fixed neural network architecture. We consider a classic method such as bisection method to implement a root finding algorithm in Julia. The algorithm is designed to find the root of the randomly generated functions of a given seed. There are other methods such as Newton-Raphson method, secant method, among others. However, we found out that bisection method give us the best result of approximating the root of the dataset. So, what is a DNN? Deep neural networks, or DNN, is a class of machine learning algorithms similar to the neural networks and aim to mimic the information processing of the brain. DNN shave more than one hidden layer I situated between the input and output layers. Each layer contains a given number of units, or in brain terms, neurons, that apply a certain functional transformation to the input. This type of model can approximate the behavior of any function to the output y of the unit I in the layer L is related to the output x of the earlier layer k with j output through a set of weights and a bias and a non-linear activation function f. So we can see the formula in the notes here. In the following code, the goal is to generate functions from the given random seed for the initial weight. The generated function will be tested by evaluating their outputs for a range of input values between -1 and +1. Each unique seed will produce a distinct function providing a wide variety of test cases. So first, in the code, we define the function of generation part, and then we set the random seed for the weight initialization. We have the function to generate a random training data, and we generate the random training data. We define and compile the model and train the model. Then we generate some sample input values, and we can adjust the number of points. So then we calculate the function outputs. Bisection method is a classic and simple algorithm that works by iteratively narrowing down the interval containing a root until a satisfactory approximation is achieved. So the theorem is if an interval on a, b, and the function of a dot the function of b is less than zero, a function of fx is found to be continuous, then there exists a value of c such that c is a member of a and b, or which the function of c is equal to 0. So why do we use the bisection method? There are multiple methods to implement the root finding algorithm in Julia as stated above. But we decided to use the bisection method because the bracketing approach of the bisection method has a guaranteed convergence. Increasing the number of iterations in bisection method always results to a more accurate root, and when comparing it to the other method, it doesn't require complemented calculation since it only need to take the average of two values. The bisection method looks to find the value of c for which the plot of the function f crosses the x-axis. The c value in this case is an approximation of the root of the function fx. How close the value of c gets to the real root depends on the value of the tolerance we set within the algorithm. For the given function fx, the bisection method works as follows. 1. Two values of a and b are chosen for which the function of a is greater than 0 and the function of b is less than 0 or the other way around. Then a midpoint c is calculated as an arithmetic mean between a and b. So next, the function f is evaluated for the value of c. If the function of c is 0, means that we found the root of the function, which is c. If the function of c is not equal to 0, we can check the sign of the function of c. If the function of c has the same sign as the function of a, we replace a and c and we keep the same value for b. If the function of c has the same sign of as the function of b, we replace b and c and keep the same value for a. Then we go back to step 2 and recalculate c with the new value of a or b. The algorithm ends when the number of predetermined iteration is complete and then the value of f, the function of c is achieved. For the bisection method code, at the initialization, we choose the initial value of the generated function fa and fb. After evaluating the function input points, we can see that fa is negative while fb is positive in this code. This means that between these points, the plot of the function will cross in the x-axis in a particular point, which is the root that we need to find. After after 40 iterations, we get fc, which is the best approximation of the root. We include the plot of fc for each unit set in the notes below. Using the appropriate Julia package and tools, we managed to find each approximation of the root for each unit set. Each run managed to find the accurate approximation within tolerance. The program will run for the iteration and we keep the last value of c as the root of our function. Increasing the number of iteration with the bisection method will always result in a more accurate root. However, it will not be productive since um, the more iteration it runs, it will be more slow. So for